Good morning, afternoon, and evening, everyone. My name is Rachel Lachinsky, and my partner's name is Santia. We are from Group 27, School of Computer Science, Pinus University, and we will present our research on theft detection methodologies using artificial intelligence. Next. Our research aims to identify theft detection methodologies using artificial intelligence, specifically deep learning techniques. We compared two of the most popular methods, which are YOLO V5 and VGG19. The goal of comparing them is to identify the most suitable method for theft detection. Next. For our introduction, we explain how theft is a big problem in our society, but regular surveillance cameras aren't always great at catching thieves quickly. They can't always tell when something suspicious is happening or send alerts in real time. The proposed research aims to systematically compare two of the most used artificial intelligence algorithms for theft detection using surveillance footage. By evaluating these algorithms based on accuracy, speed, and efficiency, we seek to identify the most effective approach for detecting theft-related activities in diverse environments. Next. So for the materials, we required personal computer hardware to train models. Second, we use Python programming language as well as deep learning frameworks for software such as TensorFlow and PyTorch. Lastly, we use YOLO V5 and VGG19 to identify how theft detection works in both models. Next. So for our related works, two of the literature reviews we collected are from Munageka and Partverde. Munageka in 2020 utilized convolutional neural network or CNN on a preprocessed surveillance footage to detect trespassing and theft incidents. The study showcased a reduction in total loss and improved CNN accuracy over epoch, successfully identifying human intrusions in cases of trespassing. Partverde in 2023 employed YOLO and FRCNN for object detection, including mask detection. The project's results also show increasingly accurate detection of thieves. Next. So the dataset that are mostly used in the literature review we collected are from USCF Crime Dataset, Weapon Detection Dataset, Snatch 1.0 Dataset, and MATLAB Dataset. Next. For our methods, we have YOLO algorithm and VGG19 model algorithm that helped us conduct research for theft detection. By using these algorithms, we made sure to create one model for each algorithm to see the results. Next. So how each method works is that in YOLO, real-time images are divided into a grid of cells with the algorithm predicting bounding boxes and probabilities for different classes. Confidence scores are assigned to these predictions, resulting in a list of bounding boxes, class labels, and confidence scores. For VGG19, it utilizes convolutional layers to extract features from video frames. The softmax function can then convert raw outputs into a probability distribution over theft-related classes. Next. So as we can see in the slide, is the result of comparison for YOLO and VGG19. For YOLO comparison result, the method is efficient, accurate in detecting objects real time, and can operate image or video frames very quickly. Unfortunately, it has less accuracy when processing multi-class objects. In some model learning, it is also not very accurate in finding suspicious objects. For VGG19, the method mostly achieves high accuracy, as well as it can classify and recognize items in real time. The minus side of VGG19 is that it has less accuracy for surveillance cameras, and it has more time complexity. Next.
The dataset that we used in the experiment to compare the YOLO and VGG19 algorithm was some image data from the UCF crime dataset, especially theft and robbery data, then image data about weapon and money that come from weapon detection dataset. Also, we added data from one YouTube video, which was converted into frame, as well as image data of snatching and theft action from the snatching dataset, which was accessed via RoboFlow. We then combine this data set into a new dataset called theft detection in RoboFlow, which was then used in our experimental model.
So this slide shows the result of YOLO V5 model training we conducted. The YOLO V5's model used 50 epochs of training, resulting in decreasing losses, which are box loss at 0.029, object loss at 0.011, and class loss at 0.003. Validation metrics showed promising performance with an overall precision score of 0.816, recall score of 0.723, and a mean average precision at 0.5. Also, IOU, MAP, 50 of 0.787. Specific class performance varied with high precision and recall for objects like knives and lower for classes like humans. These results suggest strong detection capabilities, though some object categories require further improvement. Next. So these graphs summarize the YOLO model's result from 50 epochs. The top row shows decreasing training losses of 4 bonding boxes, objectness, and class predictions, indicating effective learning. Precision and recall metrics highlight improved detection accuracy. The bottom row shows validation metrics with decreasing losses and increasing map scores, demonstrating good generalization to new data. This suggests that model maintains accuracy and efficiency. Next. So the training bounding box loss result shows that the number of loss decreased within epochs. The training object loss as well as the class loss also shows a significant lower number in each iteration. Next.
Based on the graph on the side, it shows that the accuracy of precision reached a range between 0.6 and 0.9. Based on the result of the training we carried out for 50 epoch iteration, the average precision value was 0.7, which showed the model worked quite well on the dataset we used. Validation metric also show good result with precision of 0.8 and recall of 0.7. In the validation box, the graph show that the model works well in detecting response, with the loss value decreasing with each epoch iteration. It makes it easier for the model program to differentiate the object from the background during the epoch. In the YOLO validation result, the increase in the metric or mean average precision show that the model performance is increasing every time an epoch is carried. The upward direction of the graph shows that the model is becoming more accurate in detecting and classifying objects in the validation dataset. These improvements show that the model effectively learns from training data and generalizes well to new data, so it can work in real-world application. In this slide, growth through training data, in the bar graph on the side, there is data on the class distribution of the data in the dataset, which is dominated by the crowbar class and human, are dominated by other obvious things such as hands, knife, and money. At the top right, the graph shows that the density and distribution of bounding box used in object detection. Then at the bottom left, there is a graph that shows the spatial distribution of the center of the object. Meanwhile, at the bottom right, the graph shows the width and height of the bounding box. In this result, we can see the object detection result from the YOLO version 5 model that we created, where each image data consists of various activities, background, and perspective, with a box indicating the level of detected object. In this slide, we see VGG19 training result. We also perform epoch 50 times and we use the same dataset as the YOLO model. After 50 epoch iteration, the model produced consistent accuracy of 81.87 and validation accuracy of 84.23%. The result of training loss and validation loss decreased with each iteration, so that at the epoch, the final training loss value is 0.53 and the validation loss value is 0.49. Consistent and high accuracy value and decreasing validation loss value indicate that the model is experiencing some overfitting. However, the model runs quite well on training data and validation data. Tuning or additional data is needed so that the model can develop further. From the graph below, the validation and training accuracy value do not show much change during each epoch iteration, where the validation accuracy value always has a fixed value until the end, and the training accuracy value only increases at the beginning of the iteration and has a fixed value until the end of the iteration. On training and validation loss graph, the result of each epoch iteration show that the training and validation loss value decrease with each iteration. We set the occurrence of 50 epoch, but the model stopped early 25 epoch iteration because there was no change in values in training or validation. The conclusion that we made is, based on the accuracy result of each model, our research conclusion is that the YOLO version 5 model is more suitable for detecting anomalies, behavior, and especially based on the detection object. Apart from that, the YOLO model also has later computing, so it can carry out detection in real time faster than the VGG19 model. Meanwhile, the VGG19 model will have better accuracy if it has more dataset, so the model can train to classify accurately. Based on the data set we have, the VGG19 model is more suitable for general classification and as an evaluation model that works outside the real-time time frame due to the long model computing time and requiring quite large computing resource. Thank you for watching our presentation.